under standard conditions. Ice melts at 0 degrees Celsius. And, for example, iron melts at 1,539 degrees Celsius on the same Celsius scale. It would not be much of an exaggeration to say that these values are thresholds, meaning that it is at these temperatures that the form of matter we are used to calling ice, or crystalline iron, breaks down. And it turns out the universe also has such a critical value. This critical limit is called the Planck temperature, and the Planck temperature is considered the highest temperature that can be reached in our universe. I am sure you will be interested to learn why this value is exactly what it is, why this quantity is tabulated, and what will happen if we, at least theoretically, try to approach it, or better yet, step past it, past the Planck temperature. What processes will occur, and what changes, in general, we should expect in our universe. In the case of iron, or in the case of ice, everything was more or less clear. We said a structure, iron or ice, breaks down once it hits a certain temperature, for obvious reasons. But when it comes to the universe, nothing is understandable at all. Space-time, well, will not melt by the same kind of mechanism we observe when, say, we melt tin with a soldering iron or melt iron in a crucible. And one way or another, we have to understand that spacetime is a mathematical construct, not a physical object. But even so, this mathematical construct will also fall apart at the Planck temperature. We remember, temperature measures kinetic energy for us. What exactly does measure of kinetic energy? It means that if we take an ordinary metal ball, hold it in our hands, and know that it has some structure, most likely a crystalline one, then we understand the temperature of this bar as a certain amount of energy possessed by the particles the bar is made of. We also remember that in a crystal lattice, there are lattice sites, and the particles sitting there vibrate at any temperature, even at absolute zero. Only the intensity of the vibration tends toward a minimum, or effectively to zero, when the temperature is low. That motion corresponds to the kinetic energy of those particles, and it is what we describe as temperature. In other words, temperature is a measure of energy, a measure of motion, and so on. And so in the usual case, when we heat some sample, heat a piece of ice, heat a piece of metal, heat anything at all, we eventually reach a state where the usual crystal lattice, or ordered structure, or any other kind of ordering that was there, starts to fall apart. It falls apart for one simple reason, or so they teach. You may disagree, but classical science holds that a bar, or any object, begins to break down as temperature rises because the particles start moving more intensely. Their bond energy is not enough to keep them within the existing structure, and the structure begins to fall apart. Here, in my view, the macroscopic analogies we all like to use to picture things are appropriate. These analogies suggest that if we take, say, a system of balls connected by springs and start shaking the balls vigorously, there will be some energy level of the moving balls that exceeds the strength limit of the framework, and the framework will fall apart. Something similar happens with a crystal structure, and it seems everything here is logical. Now we need to try to carry all this knowledge to a deeper level. Here, as you guessed, quantum laws start to apply. We said the particle is material, truly material, but every particle, every object, has quantum traits as well. Quantum traits mean wave function. To probe a particle, you must localize it, confining it to some volume in space. This echoes our previous video on the Planck length. I'll drop a link. Watch it. Jog your memory. Here the mechanism is similar, though the message still different. In this case, we take a single particle, which in essence is a wave function, because we remember that a wave and a particle are tied together. And what we call a particle is really a manifestation of the wave function's particle-like properties. And we understand that when we localize this wave function, it becomes confined within some volume. I just said something brilliant. To study the beetle, we must trap it in a jar. For that, we need a jar of known volume, and the beetle itself, too. Here the wave function replaces the beetle instead. For now, it doesn't matter what we mean by the wave function, or that a particle is both wave and particle. All those details aren't important right now for understanding the point today. What matters is this. Put a particle as a wave into a closed space, and wave effects activate at once. And the most interesting thing is that no matter what box we take, sooner or later we reach size limits where, one way or another, the wave function describing the particle inside the box will interact with the walls of the box. So box always presses this particle. Eventually we reach a case where a wave-like particle is confined between walls. This trapped wave shape can resemble a stretched string, say, a guitar string, fixed at both ends over a set length. And this constraint on length is connected to the Planck length limit, as you have probably guessed from everything said above. And obviously, for a particle to exist in such a box, its wavelength must be comparable to the size of the box. The wavelength cannot be larger than the size of the box. And wavelength is proportional to the momentum of the particle. So the simple logical conclusion is that the smaller the box, the shorter the wavelength, and the greater the particle's momentum. See where this is headed. It's headed again toward the idea that everything will happen now. Then finally, it starts to make sense. Because when we reduce the size of an object, when we reduce the size of the box the particle is in, the particle's energy inevitably increases. Again, simple mechanical analogies can help, though fundamentally wrong. For quick intuition, they work quite well. If an object is squeezed between walls, it holds huge energy, and that energy drives it to ricochet hard between the walls. It's like throwing a little ball into a tube and making it bounce inside. Remember those rubber super bouncy balls we had as kids? For a while they were as big as Soki, and even the legendary Dendy. Everyone had one. School kids carried them around and pelted each other with them in the schoolyard daily. So take a ball like that, or at least imagine you took one and threw it into some kind of tube where the ball can still bounce. Throw it harder, and it bounces more. That's obvious. And the shorter the length of that free run for the ball, the harder it will smack the walls, and the more slowly it will lose the energy you gave it. This is actually a very complex mechanical system, and if you try to describe it properly, you'll go crazy. But purely as a mental picture, we can compare what's happening to this ball with what we've just been saying about the de Broglie wave and about everything said above. Something called an effective temperature appears, which can be related, via the Boltzmann constant, to that very energy The word temperature did not appear by accident. I hope you understand that we are slowly approaching that very Planck temperature. So, when the energy of the object we've driven into a box starts to grow, when all of this increases, it turns out that one way or another, we also raise the temperature, because, as we said, it is directly proportional to the amount of energy. That is, one factor increases, and the other increases proportionally as well. You don't have to be a math genius to understand how simply all of this works. Basically, the main part of our explanation follows from that. Temperature is directly tied to energy, and it's tied to energy not only conceptually, but also through Boltzmann. Raising a system's temperature inevitably increases its total energy. And when that happens, we also run into an inevitable decrease in wavelength. That is, the wavelength describing a particular particle becomes smaller and smaller. Sooner or later, that wavelength reaches the size of the box in which we are trying to localize. We remember that the box is a kind of imaginary construct, but there is a real quantity, the Planck length, and sooner or later the Planck length will become equal to the size of this box that we are using for simplification. By then, the particle's temperature makes its energy reach Planck level. Something you can guess is very bad for us here. And what happens if we keep squeezing further? And if we keep squeezing further, we come to an interesting limit. We remember that, according to gravitational logic, according to what gravity actually is, we always associate gravity with the distortion of spacetime. We recall distortion links directly to energy. We recall energy equals mass. So what does mass do? In Einstein's picture, mass deforms spacetime, and the more massive the body, the greater the deformation. And what is a singularity? A singularity, for us, was long seen as theoretical. Now it's viewed as a real point where a black hole forms in spacetime itself. We are approaching a limit where the energy is maximal. That maximum energy leads to us getting the maximum mass for the given existence of the object we are considering. That maximum mass inevitably begins to create changes around itself. A constriction of spacetime. It deforms spacetime. The deformation of spacetime can reach a certain boundary, which essentially describes the formation of a singularity within those limits. And when a singularity forms, what do we get? We get a black hole again. It turns out that with increasing mass and increasing energy, we go so far that we form a black hole. And what do we need for that? All we need is for the Schwarzschild criterion to be satisfied, and then that distortion automatically turns into a black hole. And I hope you haven't lost the thread. Let's quickly go over everything we've just said. We said that if a particle is a wave, and it really is, then we can say that reducing the distance available to that wave inevitably leads to an increase in the particle's energy, according to de Broglie's hypothesis. We also said energy, via Boltzmann's constant, directly ties to temperature. As you see, it's hard to dispute that too. When we said that we increase the energy up to some maximum limit, we were saying that energy is equivalent to mass. And therefore, increasing the energy inevitably increases the mass we are dealing with. More mass isn't free. Gravity kicks in at once. Once gravity kicks in, geodesics warp inevitably, and eventually the whole system is driven toward a singularity. Once the energy, meaning temperature, gets high enough that a particle's travel length, the wavelength we mean, matches the Schwarzschild radius, we can reasonably expect a black hole to form in that extreme regime. Raising temperature will eventually open a black hole. This is exactly where the quantity we know so well comes from. This is where the value of the Planck temperature comes from. Planck temperature is essentially when spacetime and all within it must collapse into a singularity, becoming a black hole. Thus it appeared. You could argue. We mentioned the Planck length. So does Planck temperature apply only at that scale? Suppose we take some macroscopic object and raise it to the Planck temperature, if that's even possible, and it probably isn't, since the object isn't built from Planck lengths. The concept just won't work for it, so the expectation simply fails. Actually, the value we chose applies to all matter, and beyond that, to spacetime itself in every case, everywhere. All we've shown are mathematical metrics, computed values. Planck logic, overall, rests solely on calculation. Can we trust these values are correct? Yes, we can assume that, and it agrees not only with the experimental results we have for quantities where Planck scale values appear, but it also follows from plain common sense. Mathematics is not a science detached from reality. Mathematics is a science that is tightly connected to physics. Has anyone measured Planck temperature in reality? Of course not. If only because if you reach the Planck temperature, a black hole will form and swallow anything that is trying to measure the Planck temperature. Moreover, the amount of energy required to heat a system to that level is beyond anything reasonable. So all these values are usually discussed in connection with the early universe. There was, whatever the correct term is, I cannot recall it right now, the Planck epoch or something like that. And it is believed that at that moment the Planck temperature existed, along with the Planck length. And all of this was also set by the Planck time and other Planck units. Planck quantities mark the universe's earliest stage and could be observed only then, briefly there. After that, because the system changed in a certain way, because it evolved in a direction we are familiar with, the Planck units moved into the background. They remained as an insurmountable boundary, but for us they are unattainable now. So, in principle, we will never be able to measure the Planck temperature, at least using the approaches we have today, the current level of knowledge, and the information available to us. Question everyone asks: what lies beyond Planck temperature? How will the system behave? Here we can't even guess, because our physics, mostly built on math, starts from the idea that Planck scale values mark an impassable limit for us today. We don't know what physics is like there. We don't know the temperature there, or if it's even temperature in the physical sense at all. We have already said several times during this conversation that temperature is the kinetic energy of particles, a measure of the motion of particles inside a body. And at the Planck scale, at the Planck temperature, it may turn out that bodies themselves stop being bodies. And if we really end up somewhere near a black hole, if space-time really behaves that way, then there will not be matter. So temperature doesn't apply in that region. It doesn't mean nothing exists there. It doesn't mean the universe ends there. It means nothing at all, either. It means that our physics, which is built largely on calculations, stops working there. We don't know what physics we must deal with there. We don't know how nature behaves, what systems are involved, or even what it all looks like. For that reason, we should not say that nothing exists above the Planck temperature. We should say that our very understanding of temperature is limited by the Planck scale. Agree. Those are two very different things from simply saying, oh, nothing exists there. So, I think this information is enough for you to correctly understand what the Planck temperature is and what it is not, what happens in nature at that scale, and what does not happen. Thank you all for your attention. Until next time, all the best to you. And here we are talking about physics on the border with philosophy. Until next time, and goodbye, everyone.